Okay, so in this lecture we'll talk about how to manipulate spin. That is, how do we actually implement quantum gates on our spin qubit. Alright, so let's first try to understand what a quantum gate looks like on the Bloch sphere. So why do we do this? Well, because remember that in order to understand how the spin qubit interacts with the external world, we have to locate the spin qubit on a Bloch sphere. Okay, so the answer is actually very elegant. What it says is that a quantum gate or a unitary transformation on our qubit state is performed by a rotation of our Bloch sphere about some axis. So in other words, we pick some axis and we just rotate this Bloch sphere through some angle about this axis. So let's see an example of this. So we have a bit flip gate, which we denote by x, which is given by this unitary transformation. And what does it look like? Well, in our two-dimensional Hilbert space, what it looks like is this. So what we do is we actually rotate the two-dimensional vector space about this 45-degree axis. So remember, this is just the real representation we are looking at, the two-dimensional plane. But of course, we are working in a two-dimensional complex vector space, and so it's a rotation through pi, a pi rotation about this plus state. And what it does is it swaps 0 and 1. Now, the corresponding thing we are going to do on the Bloch sphere, well, let's locate where the 0 and 1 states and the plus states lie. So the 0 state sits out here in the plus z axis. The 1 state is antipodal to it. So this is where the 1 state sits. And the plus state is just plus x axis. So now what we want to do is we want to actually take this Bloch sphere and we want to rotate it about the x axis through 180 degrees, a pi rotation. And what that does is it actually takes this sphere and it rotates it. So the plus z-axis actually rotates all the way down and comes to the minus z-axis. So what we get is this flip where 0 goes to 1 and 1 goes to 0 and plus stays where it is. Okay, so the moral of all this is that we want to be able to rotate the Bloch sphere about some axis. So how do we do this? Well, answer lies in the fact that our spin makes the electron behave like a little magnet, and we can grab hold of this magnet by an external magnetic field. So what we're going to do is we're going to take some large magnetic field, say pointing up, pointing in the plus z direction. So let's say it's a field of magnitude B0, so it's a B field, and it's pointing in the plus z direction. So now, how does our spin interact with this external magnetic field? Well, really what we're asking is, what's the Hamiltonian? And let me tell you the answer. The Hamiltonian is E over m h bar over 2 sigma sub z B0. Okay, what's sigma sub z? Well, sigma sub z is just, it's also what we call z. It's a Pauli spin matrix. It's just a phase flip. So remember that the electron is a spin half particle. Its spin takes on one of two values. And in fact, these two values are plus h bar over 2 and minus h bar over 2. So the spin observable in the z direction is just h bar over 2 times sigma sub z. So that's our observable, that's the spin in the z direction. And then we multiply by E over m. So this is what gives us the magnetic moment, and we are multiplying that by B0. So that's a Hamiltonian. And now, if we wanted to understand how the spin behaves under this Hamiltonian, then of course what we would do is we'd solve Schrödinger's equation, I d by dt of psi of t is equal to h psi of t. Right? So if you want to know what's the state of this spin qubit as a function of time under this Hamiltonian, we'd actually solve Schrödinger's equation. And let me just tell you the answer, and then we'll sort of get some intuition about where this Hamiltonian came from and how to solve the Schrodinger's equation. But let me first tell you what the answer is. So let's say that this is psi naught. This is what psi at time 0 looked like. It was pointing in this direction where theta and phi. Well, then what happens to the spin is it just goes ahead and it stays at the same angle theta. It keeps the same angle theta with the z direction, but now it starts precessing. So phi actually changes as a function of time. So what it does is it just goes ahead and precesses, and so the angle phi changes as a function of time, and it just keeps precessing as a function of time, and it precesses at a certain rate, omega sub L, which is E B naught over M. This is called the LARMOR frequency. And so this evolution of the state of the spin is called LARMOR precession. So now, of course, if you wanted to carry out a certain gate where you were rotating about the z-axis, and if you wanted to rotate through an angle delta phi, then of course you would choose to turn on your B field pointing in the z direction for a time which is delta t, so that the Bloch sphere actually rotates through an angle of delta phi. So since it's rotating, this is the frequency, you choose delta t so that it actually rotates through that angle. Now, of course, there was nothing very special about the z-axis. We could also point the B field in some other direction, and then the Bloch sphere would actually rotate about that. You know, it would precess about that particular axis. Okay, so this gives us a prescription for how to actually carry out any arbitrary single qubit, arbitrary gate on a qubit state. So now let's try to understand where this Hamiltonian came from, and then how do we actually solve it to see that the spin actually precesses about the z-axis. So it's a hand-waving sort of explanation that I'll give you. It's going to be sort of classical intuition about where the magnetic moment comes from when you have a spinning charge. How does it come from this angular momentum? So remember that the energy of a magnet mu, so suppose you have a magnet with magnetic moment mu in an external field B, then its energy is minus mu dot B. Right? So meaning it wants to align with the external field. Now, where does the magnetic moment come from? Well, usually it comes from a spinning charge. So let's say that you have this charge that's moving around in a circle of radius r. And let's say that that's the amount of charge that goes around in one rotation. Okay, and let's say it's moving at velocity v. So the total amount of charge that passes by, every time it makes a full rotation, you have charge E that passes by any particular point in time, any particular point on this circle. So now we can figure out what the current is. So the current is just going to be its current over time, right? It's charge over time. So how much time does it take for this current to actually go past a particular point? Well, the time it takes is just 2 pi r divided by v, right? Distance over speed. So it's just ev over 2 pi r. Okay, but now how does this current correspond to the magnetic moment? So the magnetic moment is current times area, which is just ev over 2 pi r times pi r squared. So you can get rid of these. So it's just EVR divided by 2. Okay, but now we want to relate this not to V and R, but we want to relate it to angular momentum. So what's the angular momentum? Well, angular momentum is just mvr. And so what this means is v times r is just L over m. And now substituting, we get it's E times L over 2m. And so, in fact, what, if you write it out, mu is minus E L over 2m. And so you could substitute that back in here to find that the energy is just E L B over 2m. Okay, so now you can compare this expression to our Hamiltonian up here, and you see you get E over m. L, which is the angular momentum, is just h power over 2 sigma z in the z direction, and so we are taking that times the external field. The only mysterious thing here is this factor of 2, and the point is that in the quantum case, okay, so you do get this factor of 2, and then there's a correction factor, which is called a G factor, which for an electron, so this G factor is a unitless correction factor in quantum mechanics. It's 2 in the case of electrons, and it's about 5.6 for protons. And so since we are working with electrons, we'll just strike it out, and that's our Hamiltonian. Okay, so this was just a hand-waving explanation about where we got this Hamiltonian from. All right, but now, once we have this Hamiltonian, we need to solve it. So what does it look like? So let's write it out again. So we have the Hamiltonian is E over m h power over 2 sigma z times b naught, which is E divided by m h power over 2 b naught. It's just some scalar, and then sigma z is 1 minus 1 0 0. Okay, so that's Hamiltonian. And now remember what happens. Well, we want to, let's say psi naught, psi at time 0 is just alpha 0 plus beta 1, and we want to know what's psi at time t. Okay, so our prescription for figuring out how the state evolves is just to compute the eigenvectors and eigenvalues. Well, so what are the eigenvectors and eigenvalues of H? Well, clearly they are just 0 and 1. What are the eigenvalues? Well, they are E h power over 2m b naught and minus E h power over 2m b naught. Okay, so if you follow the prescription that we had from solving Schrödinger's equation, it's e to the minus I lambda, which is E h bar b naught over 2m divided by h bar, plus beta, this is times alpha, and plus e to the minus this, so you get plus I E h bar b naught over 2m divided by h bar beta 1. Okay, so these h bars of course cancel, and now we can pull out e to the minus I E b naught over 2m. We get alpha 0 plus e to the I E b naught over m. Sorry, there should have been a t in all of this. T beta 1. Okay. All right, so now remember we said omega LARMOR is E b naught over m. This is an overall phase, we can just ignore that, and so we just get alpha 0 plus e to the I omega sub L t beta 1. Okay, so that's what the state of the qubit, a spin, looks like at time t. But now let's try to understand what it looks like on the Bloch sphere. So let's say that our initial state was cosine theta over 2, 0, plus e to the I phi sine theta over 2, 1. So now our state at time t now becomes cosine theta over 2, 0, plus e to the I phi plus omega lt beta 1. And so you can see the effect of this evolution of the qubit state at time t is just that phi changes to phi plus omega lt. So the phase phi precesses at a rate which is omega l. And this is our LARMOR frequency.